what if we have a reaction? So here, let's just look at the reaction where we have some chemical A reacting with B to produce C. And we have the stoichiometric coefficients of A, B, and C. So A moles of A react with B moles of B to produce C moles of C. We can write an equilibrium, sorry, we can write a reaction rate expression. So the change in C with respect to D is equal to some rate constant times A and B. Okay. Now, M and N are not based on the stoichiometric coefficient, except in some very, very special cases. M and N are empirically derived. So you've got to obtain this information from the empirical data. Now, if the rate is only dependent on one reactant, let's say A, we can write a more simplified expression. We still do not know M unless we experimentally determine M. For those of you in 480, you'll actually do an experiment where you will determine the rate kinetics. Now, if M is equal to 1, then the reaction is first order with respect to A. It's 0 order with respect to B. And we can write an expression that says that the change in C with respect to T is equal to a rate constant and times the concentration, in this case, the concentration of A. Now, we've just written the same expressions, which I just gave you. Now, if A here is equal to C, then the rate of change in C is equal to minus the rate of change in A. So as C increases, A is decreasing in a proportional amount. And we can write this expression that change in A with respect to time is equal to minus K times A. This essentially is the expression that we will use throughout the rest of the course to describe first order rate expressions. So many environmental reactions can be described with first order kinetics, or what we call pseudo first order kinetics, and that's where one component is in a much higher concentration than the other. So basically, its concentration is essentially constant, so we can describe it as what's referred to as pseudo first order. Again, if you're taking 480, you'll cover that to greater extent in 480. I'm not going to go into details here. But now, going back to our mass balance, we have the same mass balance expression that we've had. Now we add a reaction term. Now we can describe this as either positive. So if it's positive, you have formation of whatever chemical you're looking at, or you can also use it for microorganisms. If it is negative, then we have decay. So we can write this expression. So this is our rate expression here. So this is our mass. This is our mass balance. And this is our kinetic expression. This, we replace this term here with this expression here. We end up with a term here, V times Kc. So it's the volume times the first order rate constant times the concentration. And this here is going to be the concentration in the reactor. I've put up another poll. As we talk about this, we've been talking a lot. So you should see the results. Okay. When your change in mass with respect to time is equal to 0, the system is at steady state. Okay. When we talk about equilibrium, we're talking about a chemical reaction. So for instance, there, if we look back at the chemical reaction we wrote for the general reaction, if this is at equilibrium, there's no net change in the concentrations of these species here. But if we're talking about, when we're talking about rate of accumulation, we're looking at a reactor system, okay, and we're looking at the change in mass in that system. So when the rate of accumulation, change in mass with respect to time is equal to 0, we're talking about steady state conditions. So we have our mass balance equation. If again, we'll assume completely mixed reactor, so we have the CSTR, so the concentration in the reactor is equal to the concentration leaving the reactor. We'll assume that the volume is constant, and we'll assume that the compound decays according to first order kinetics. So our K will have units of inverse time. So we can write our mass balance equation here. Our mass in is equal to Q times C in. Mass out is Q times C out. And because we have decay, this term is negative. It's a net loss. And we've said volume is constant, so we can factor out volume from the differential. Now, if we integrate this from C0 to C sub t, and from T0 to time t, we have this general form of the equation. It's more complicated than before because now note we have a K term in the exponential, and before this was just C in. Notice if you don't have a K, then the Q over V factors out. Okay? So where we have reaction, this is the equation we will use. So now, if we have the same problem that we had before, except now we have a substance that is degrading with a rate constant. Okay? So we start out with pure water, with clean water. So C0 is equal to 0. We're going to pump in, now we're going to pump in a reactive substance, same concentration as before. Flow rate is the same as before. And now the substance degrades according to first order kinetics, and we have a rate constant of 0.25 inverse days.
Professor Maston?
Yes?
Can you go back to the previous slide?
But just note that, like I said, if you don't have K, then this equation is exactly the equation that we had before for a non-reactive substance. So if K is 0, it's the exact same equation. So we have the exact same system before. The only difference we have is that instead of a non-reactive substance, we have a reactive substance. So in this case here, how do you think the graph will change? How will it compare to the previous graph? Steady state concentration. Will it be the same as before? 100 milligrams per liter? Okay, so we have steady state will be at a lower concentration. It will slowly go down. Okay. Now remember, we start with a clean solution. So here's my graph, and I have concentration with time. At time 0, we have concentration 0. Okay, so that instantaneous point in time as that pump is turned on. Before it went to 100, it's going to be less. Okay, let's look. So here, notice here, our steady state concentration is about 28.6 milligrams per liter. And the time that it took to reach steady state is much less than it was before. So before, it took about 40 days. Here, by 20 days, you've reached steady state. So let's just go back. I didn't include it here, but let's write the mass balance expression. So we have the change in mass with respect to time is equal to mass in minus mass out minus mass reacted. Since volume is constant, we can write volume dc dt is equal, and since Q, volume is constant, we'll use Q, so we have C in Q minus C out, Q minus K. This C is our C out times the volume. And then when we integrate this from C0 to C sub t, and from time 0 to time t, we have the equation. I'm not going to write it out, the equation that I had before. And then we can use, I just did it in an Excel spreadsheet. I can then determine the concentration at any time. So this is C at any time t. What if instead of having a pure solution initially, we have a 50 milligram per liter solution? So what we change now is we have a 50 milligram per liter solution. This is C, same reactor. We turn on the pump. We're going to pump in the same reactive substance, 100 milligram per liter solution, just as before, same flow rate as we've used, same rate constant. What's the steady state concentration? Absolutely correct. So here we're going to start at 50. That's the initial, and it's going to decrease to the same concentration. And we're back to the same concentration. So here we are. So it starts here, decreases, and it's 28.6 milligrams per liter. So this was a situation where we had no reaction. Here we start, C naught is equal to 0, and we're pumping in 100 milligram per liter solution, and the rate constant is 0.25 inverse days. Here we start with C0 equals 50 milligrams per liter. Same situation. Same reactive substance that we're pumping in. And we end up at the same point. What if the initial concentration were 100 milligrams per liter? So what if instead we have, let's just add another one. Okay, so C0 is equal to 100 milligrams per liter. So if we start out here, we will end up with the same concentration right here. I want you to think about that. I'm going to stop here. Okay. I want between now and Wednesday, I want you to think about that. Okay. So the steady state concentration is independent of that initial concentration in the reactor. It's dependent entirely on what you're pumping into the reactor and the rate constant. Think about that mathematically. Okay, we can go back. You've got 0 equals your mass in minus mass out minus the mass reaction. Okay, think about that mathematically. And think about that physically. What does that really mean? And how is that going to affect our systems? For the most part, in water and wastewater, we operate at steady state. We actually don't care about the initial condition for the most part.